So here's the weird part, and it took me quite a while to wrap my head around this, is that if I can compare a series to an integral, and the integral converges, right, the series converges. If the integral diverges, the series diverges. And it doesn't make a lot of sense at first to think about that second one. So typically, when I give you an integral test on their final exam, it's going to converge. Because I don't care about the problems that diverge anyway, right? So I want to make sure that you're able to find one that does converge. So, but the idea is, and let me write out terms here, right? What is it? 1, and then 1/2, yes? 1/3, 1/4, etc., right? But what I want to do is I want to plot. So when n is 1, I get a height of 1, right? When n is 2, I get a height of 2. Sorry, 1/2. Yes, you with me? So these guys are my heights. But what I'm going to actually think of them as areas, okay? So I'm actually going to draw the square, or at least that piece of it, right? Does that make sense? Because my base is 1 every time. So this is now an area. It's a 1 by 1 square, and 1/2 is a 1 by 1/2 rectangle, right? 1/3 is a 1 by 1/3 rectangle. Yes, you with me? So, and then on top of that, I'm drawing my f of x of 1 over x, right? So it's funny, though, right? Think about this. We know this one diverges. So, but we have to be able to think of this series written as a right-hand rectangle or a left-hand rectangle. So in this place, it doesn't make a lot of sense that the series diverges, right? It doesn't make a lot of sense that the series diverges because it looks like the sum is underneath 1 over x, isn't it? Yeah, right? So we know for sure that the integral from 1 to infinity of 1 over x dx is a greater sum than that 1 over n, right? Okay, but the integral test says if my integral diverges, the series has to diverge as well. So what we do to get the understanding of it is not use this set of rectangles, but use the left-hand side rectangles. So I'm drawing one more time the same idea. 1, 2, 3, 4. Right, my heights that I had, 1/3, 1/4, yes? I'm drawing my integral test in, so the integral of 1 over x, yes? But I'm going to draw my rectangles with right-hand rectangles. And now it's easy to see the divergence of this. Right? Look at the red area. Can you see that, Noah? Yep. Look at that red area compared to the purple area. Right? Do you see that the purple area is above? And I know the red area already diverges. So, and I'm not cheating this. This is the weird thing, right? Because we're going on this side. When I drew it the first time, I did right-hand rectangles, meaning the top right corner of my rectangle hit the curve, right? And so it's clear that I could draw either set of rectangles, right? So if I made this one 1 over x squared, and I know that one converges, right? That red area here converges, and then I just have one more finite area here, in fact 1 by 1, right? So plus 1 to the sum. and I still get something convergent. Now, so what's the difference? If I draw left-hand rectangles or right-hand rectangles, I have to be able to think of both of them to think of the divergence and convergence. Is that making sense at all? Because it felt like I was getting cheated when I first learned it. It felt like it's saying, well, can't I just make anything happen that I want to happen? No. But in order to really kind of get the geometry of what's happening, when you're talking about a divergence one, you want to draw these left-hand rectangles, right? See, each rectangle hits the curve on its left top corner, right? And for the convergent one, I want to use right-hand rectangles. All right, let's do a couple of problems.
Right, and if you use the wrong one, it's just
It's inconclusive. Yeah, because and that's a great thought there, because if I did draw the left-hand rectangles for 1 over x, right? I already know that this piece is divergent, right, from 1 to infinity. And my sum is smaller, right? Okay, but then I'm going, but it doesn't tell me anything. Because if I know that what I got is divergent, I know something divergent, but I also know something smaller doesn't mean it's convergent. Just because it's smaller, right, doesn't mean it converges. That's right. So anyway, let's look at a couple of problems. So we had that P series, but it actually works for where's my integral test? Sorry. Thank you. 577?
Yeah.
Really? Oh, yeah. There it is, yeah. Yep. So, right, again, I said it. The thing that's important here is that I must have a function that's positive and decreasing. Okay? Must have a function that's positive and decreasing. All right, let's do some integral test problems. So basically, all the way from 11 to 30 is I'm pretty sure these could be done that way. Let's go to 15, right? So 15 says the sum from n equals 1 to infinity of n e to the n, e to the minus n. Look familiar to you? Yeah. The sum from n equals 1 to infinity of n e to the minus n. And this is, I did n squared e to the minus n before the test, and then I put x squared e to the minus x on the test, right? So let's write out some of these terms here, because I want to be able to think about them, right? What do I have? 1 e to the minus 1 plus 2 e to the minus 2 plus 3 e to the minus 3, right? I'm just writing them out just so I can get an idea of what's happening. It looks like I have 1 over e plus 2 over e squared plus 3 over e cubed, etc., right? Not that I really care too much about this. I know it's some decimal. I know they're positive, and for sure they're getting smaller, right? For sure they're getting smaller, yes? Each thing I'm adding is getting smaller. think about it. If things were positive and negative, I'm going to get confused. Things are going to cancel out. If things are getting bigger and I keep adding them, of course it's not going to diverge, right? I'm sorry, of course it's not going to converge. I'm going to keep adding bigger and bigger numbers. So it's pretty obvious that this guy is positive and decreasing. Of course, I could do the derivative, right, to show that it's decreasing, to show that the derivative is always negative. Nice. So, of course, we're going to draw y equals x e to the minus x. I don't think that's right. No. I think the right-hand side is right. I think the left-hand side just shoots down, but let me not guess. Yeah. Nice. And I only care about from 1 to infinity, right? So I can do that with a curly bracket and x greater than 1. I mean, you can't tell that the point, what is the point there? 1 comma 1 over e, right? So even though I didn't use the equal sign here, that point is there, I guess, and I can use that equal sign. It just takes a little bit more work. I got to use the the palette. Where is it? There it is. There's the greater than equal. But you can't, either one I put in when I'm restricting my domain, you can't see it. You can't see a point, right? But I put it in there anyway. Remember, 1 over x diverges, 1 over x squared converges. I always like to put this in as a quick check, y equals 1 over x squared, just because it's easy to think about, right? It's easy to think about. Look at what's happening. Do you see what's eventually happening? 1 over x is above this, then it dips below it for a brief time, and then it goes back above it again, right? So you can kind of cheat it there. Probably very hard to see it, but you can kind of see the blue line coming back down underneath the black line there, right? So since it's a finite amount of time that it's above my thing that converges, I can just chop it off there and know that that part is obviously finite and the rest infinite but convergent, right? So we're going to do an integral test to show that this thing converges. So we want the integral from 1 to infinity of x e to the minus x dx. Good. How do I do it? By parts. Nice. So, Leote, I know u must be x. Why? A comes before e in this word, this made-up Calc 2 word. So, algebraic gets the u sub before an exponential gets the u sub. This one also is a shortcut, correct? This is a shortcut. If I pick my value of u and keep differentiating and eventually I get a 0, I know I can take a shortcut, right? So let's shortcut it. So I need the sine, I need the u, I need the dv, plus minus plus should be enough because x, 1, and 0 is gone, right? So I took my value of u, put it there, then kept differentiating, right? With the dv, it takes a little bit more work. I know that dv equals e to the minus x dx, right? And so when I integrate, I get v equals the opposite of e to the minus x. Do you agree with that? Do you need to see that? Do you agree with that, or do you need to see it? Need to see it? Yep. So so going back to here, I can let u be negative x and du is negative 1 dx. So you can see that I need to create a negative on the inside, so I cancel it with a negative on the outside. Right? Those two negatives out there cancel, right? So it's the original function. But this is now e to the u du. Right? The e to the minus x is e to the u. The minus 1 dx is du. Okay, but the antiderivative of e to the u is e to the u. So there it is, the opposite of e to the u, which of course is the opposite of e to the negative x. So every time I integrate now, I'm going to get that negative canceling, right? Every time. So that's what I'm writing here. Even though I don't need the last one, but every time I integrate, I get another negative out front. Does that help? Okay? Yep. So this is the piece I need. And it looks like I have a negative on every term, right? So I have negative x e to the minus x minus e to the minus x. I forgot my limit, and I wrote that on some of yours. When you're doing these things, you need to put it in limit notation, right? Sorry about that. So I should have had the limit as a goes to infinity, right, of the integral from 1 to infinity of x e to the minus x dx equals the limit as a goes to infinity of my solution, right? Negative x e to the minus x minus e to the minus x from at a and at 1, right? Yes, you with me? So when I see that infinite limit, that improper integral, I've got to write it as a limit, right? I've got to write that as a limit. Well, and I'm trying not to confuse you. I like to evaluate my integrals a little differently. I see that I have everything as a negative. I'm going to do my second evaluation first because it's going to cancel the negative, right? Evaluate at a minus evaluate at 1. So I'm going to minus evaluate at 1 first, right? And so what is that? 1 e to the 1 minus 1 plus e to the minus 1. And then minus my limit. My limit, I'm going to factor out the negative. It's staying the same. Remember, I'm just going to evaluate it at a. But what do I have? I have e to the minus x times x plus 1. And this part is where I need what? L'Hopital's, right? But what happens to e to the minus x as a goes to infinity? As x goes to infinity, it goes to 0. So I have a 0 times infinity here. Are you with me? I have a 0 times infinity. I need infinity over infinity or 0 over 0. Which one looks easier to move? The e, right? The e to the minus x, yes? Doesn't mean it's always the right one to move, but in this case it is. I actually, I already evaluated it at This is A, sorry.
Can you,
Yeah,
separate out the one?
exactly, yeah. Right? I already evaluated. I just forgot to put the A in up here. Sorry. That should have been going in there. The ones went in here, right? So now I'll just say hop, or I could see you do this as another alternative of writing like this. I could say I'm doing the limit of a plus 1 prime over e to the a prime. So that's fine too. Just write that you're going to do L'Hopital's rule or put in the derivative notation. Right? Either one is fine. So the derivative of a plus 1 is 1, right? So minus the limit, as a goes to infinity, of 1 over e to the a. Now it's 1 over something going to infinity. So we know, right? We know that goes to 0. So done. So converges. So since the integral converges, we know the series converges. Do I have to do anything for a problem like this to cover material from chapter 5 and 6? No, right? So if you're going to do this integral test version, you can do the problem, what was it, problem number what on the exam? It was problem number 2, right? It's problem number 2. And you're going to make sure you write it as a limit. You're going to make sure you show me L'Hopital's rule. You're going to make your integral test conclusion. Since the function, right, the limit of the function converges, I know the series converges. I have to make sure the function is positive and decreasing, right, in order to use the integral test. Yep. Yeah, so I plugged in the 1 here, right? So 1 e to the minus 1, that's 1 over e, and a minus e to the minus 1, right? And so, yeah, so there's a 1 over e and another 1 over e, so it's 2 over e. Yep. Yep. Let's look at another one here. Oh God, look at 16. No, not really, right? You see 16? What is it? What is it hinting at? It's partial fractions, right? What about 30? Yeah, it could be. I don't know. What's that? I know, I know. Hmm. Let's try 30. It looks tough. So n squared minus 5n. Oops. N cubed plus n plus 1. sorry. I'm not supposed to be writing it as an integral, right? It's the sum. Right. So we want to try and do an integral test here if possible. We do have other options for tests, okay? And we'll talk about more of them this week, but this is the particular one that we're on. We want to compare this to, right? The integral from 1 to infinity of x squared minus 5x over x cubed plus x plus 1, if I can. What do I have to make sure first? I have to make sure this function is always positive, right? So I might as well start writing out terms and see what I get. And I want to make sure it's also decreasing. If it's not, I can't use the integral test. So help me here. What do I get? I get 1 minus 5 over 3. Uh-oh, that seems like trouble, but if I only have a few negative terms, I'm fine with that. I can start to use this integral test once if it ever recovers here. So what do I get when I put in 2? 4 minus 10? 2, right? 8, 10, 11. Of course, why didn't I stop wasting my time and go right away to my Desmos, right? I'm searching for Noah here. Oh, nice. Here's the file. Thank you. So I'm going to change this guy, right, to n squared minus 5n over n cubed plus n plus 1, right? Ah. Nice. So looks like I have 3 or 4 finite pieces that are negative, and the rest are positive. Are they decreasing, though? That's the question I really want to know, right? So a few finite ones of negative is fine, because I can add those up and then ignore them, right? Add up see if the rest converges, and just know I've got definitely something that else converges. I don't know if this is a integral test though. Let's see, when 3 I get what, 9 minus 15 upstairs, and then 4 I get 16 minus, oh no, 4 is yeah, 16 minus 20. Is it still negative? What's next? 5 is 25. Oh, there it is, 25 minus 25. It should start being positive now. At 6 is what, 36? There it is, 36 minus 30. So there's 1, 2, 3, 4, 5 terms that are negative, and then they start to be positive. I have to make sure it's decreasing. I think the easiest way is to take the derivative. But downstairs function is, upstairs function. Downstairs function is x cubed plus x plus 1. I'm doing a quotient rule here, yes? Hopefully you're doing it with me, racing me. Yuck. Horrible. Oh, pretty nasty. You guys don't need practice on quotient rule? No, minus. I'm trying to do too much at once here, just because I'm getting bored. X to the fourth minus 10x cubed. Oh god. Minus x squared minus 2x plus 5. Sorry. I don't think this is the way to go. Notice everything I'm doing, it's making it more complicated. I guess I want to make some conclusion that this thing I cannot do the derivative test with it. Now, what do I want to really do? Downstairs is always positive for sure, right? So I just want to see at what point this thing starts to become negative. So I'm quitting trying to do it algebraic, and I'm going to go right into Desmos now. Anybody have that handy? You can read it to me. Is it just x to the fourth? Is that right? Minus x cubed? 10, what is it? 10x cubed, thank you. Minus x squared. Thank you. Plus 5. Yeah, it's not good, right? Definitely not. I can't use the integral test on it. Remember, if the derivative is positive, right? If the derivative is positive, this says the function is increasing. So it looks like after 10, it's increasing for the rest of the time. I need my function to be decreasing, right? So can't do the integral test on that, but that's okay. All right, let's take a little break. Let's take 18 minutes. Go ahead. What were you going to say? But the bottom half is always positive, right? So it's not going to change the sign of my derivative.
Oh, yeah.
Right?
Yeah.
So that bottom...
Thinking the derivative won't go to 0.
Right. But, exactly. So the problem is, so that piece downstairs doesn't change the sign at all, right? Because if n is bigger than 1, obviously x cubed plus x plus 1 is still positive, and then I square it anyway, right? So only the numerator's giving me my sign. I needed my derivative to be negative because that tells me it's decreasing, and it was not. Yeah. All right, let's take a little break. Let's take a 17-minute break, come back at 9:30.